Okay, so this is the exact time and place for us to have the 3 course, right? Okay, so it seems there are not so many people here, or is this the regular amount of people coming here in the previous weeks? I had assumed that there probably would be fewer people coming here if we use a substitute instructor this time, but I had not been expected that there will be 3. But anyway, then, so let's continue. So in this week we'll be talking about chapter 12, grids, and frankly speaking, this is one of the topics that I'm not so interested in, because this is one of the most, non-algorithmic part in this book. So, anyway, since Professor Skiena wanted me to take this course, I just take it. So, I'll be first reviewing the assignments we had be given out in the previous week, and then I'll be covering the topics in grids. And since if you had read the book before, you would see that this topic, most of the things covered in it are just some mathematical tricks that are not so complex. So I assume we would be able to finish a little bit earlier, and then I would be spend some time on some analysis of some recent ACM ICPC World Finals problems. So for a review of assignments in chapter 3, there are 4 problems. So and there are 3 persons here. So the number of problems is a little bit larger than the number of persons. So did you all solve all of the problems, or how many problems have you solved? 2, and 1, 4. Okay. So, are there any specific problems you'd like to mention in solving last week's problems that made you unsuccessfully to solve them all? Like, so which problem did you solve? The first one. Okay. So the first one. Okay, and you?
The first and third.
The first and third. Okay. Okay. So about the problems, the first and the third. No, the first and the third. Right. Okay. So, how many problems did you solve in your last week's assignment? 4. Thank you. 1. Okay. So the first problem.
Yes, the first one.
Okay.
This one I've got for the floating point precision problem.
I see. So let me see. So is it because of an algorithmic problem? Because is it because of you are not quite sure of how to solve this problem, or is it because of you are quite sure of how to solve this problem that you're unable to make it accepted?
It just seemed like a lot of work, so I didn't try.
I see. Okay, so And for this one might be the most difficult problem in the previous week's assignment. Yeah.
It's the simplest because you can explore fast to solve this. My algorithm is n factorial times n squared efficiency, but it's still possible.
Yeah, I mean the time complexity is no, because the input constraint is only 8. So I mean the most difficult, because the most difficult, this adjective is used to compare with the other 3 problems.
Actually, the server is harder.
Which one is harder?
The first decade problem.
This problem?
The first decade.
The first decade problem. Actually, I don't think this birthday cake is hard, because I think we can have let me see how many there are in cherries in we can first prove that the optimal line or the line that satisfies the requirement would only be a small delta compared to it can cross a line. No, it cannot cross a line, but it can be only a very small shift towards the one that passes a line. Right. Yeah. And then for each cherry, there are only 2n cherries, so there are around, say, n is there a pen here? Oh. I had forgotten that it should be me who should be able to prepare these. So is there anybody here who can provide any kind of material that can help us to write on the board? Or there's nothing? That's simply amazing, thank you. So for this problem, we have a circle, we have a number of cherries, and we want to draw a line through the origin that can split the cake exactly into half. And we want to ensure that we have the same number of cherries in both parts of the circle. So I had one simple sort of this problem is that the line should be in the form of ax plus by equals to 0. And then if we enumerate through all possible a and b, we have around 1,000 squared, that is 10 raised to the power of 10 possibilities of all the lines. And then for each of the line, for each line, we have to test the number of cherries on the left half of the cake. So this is around modifies 100. 10 raised to the power of 8. It's a little bit slightly over the time limit, but it should be okay. But it's also simple to prove that the line we would want should be something like this. Say if we have 4 cherries and there is a line passing through the origin here. So we could try to move the line a bit by making it does not cross any cherry. That means the number of lines we have to test can be reduced from around 1,000 square to around 100, and that is the number of cherries, and that will be okay. So that's how I want to solve this.
There's a lot of special cases for this problem.
For example,
If cherries on the y-axis, or the lines of the y-axis, and a lot of things.
if the cherries are on the y-axis,
Maybe it's because of my algorithm only care about anything.
I see.
So
So that's so one of the major reasons for you to have special cases is how you handle the form of the line. Yeah. If you use something like y equals to kx plus b, and then for all the cherries falling upon the, let me see, it's let's see, it should be the y-axis. There'll be a problem. Anyway, so this problem might be a little bit ad hoc, and for this problem, it's easy to see that m is less than 8, so we can enumerate all the possibilities. So the next question remaining is, if we have one permutation of these circles, how do we know the length of the rectangle that can cover them all? This again is a simple high school mathematics problem that might take a while to solve, but it's still easy. You see that so this part is R1, this part is R12, this part is R2, this part is R2, this part is R1. So we have a right angle here. We have a right angle here as well. So the problem is how we determine this x. Since if we only have two circles, the length of the rectangle at this side is this R1 plus x plus R2. And to solve this x, we have R1 here, R2. So if we have an equation, this is R1 minus y, this is R2 minus y. So we have this using the Pythagoras principle, and this should be R1 squared plus the R2 squared part should be equal to x. Just one equation. So another equation. Let me see.
this problem is simple. You just try from the leftmost to this position, and set the rightmost position of this circle. And the rightmost circle will be the right edge.
Then I mean, if I have a specific permutation.
Yes.
Yeah. So how am I going to determine this? Yes, here.
I can write it.
Okay.
First, this is the left part of the problem. So, for example, I already have several circles here. Those positions I know.
Yeah.
Already chosen. When I want to put the next one, first I put in here. I have
to say you just try to put it in this way so it is tended to the y-axis.
Yes.
And then try to move it to the next position. Okay, I see. So for this problem, it's you can try it in such a way, and I'm thinking if there are other approaches. Okay, so these are previous week's assignments. So about this week's lecture, I would be rather using Skiena's official lecture slides. If you had read the so if you have read these parts before, you'll see they are actually very easy. Another problem is that, can you guys provide anything for me to? So for what? Oh, so the topics we're going to cover in this chapter would be linear grids, triangular grids, hexagonal grids, and these longitudes and latitudes part. Again, most of these parts are some tricks of the high school or even middle school mathematics. So first about linear grids. We can simply view linear grids if it's on a two-dimensional plane as a two-dimensional array. So one of the problems is for each vertex, we can see that it would touch for a vertex in a d-dimensional rectilinear grid. So it would touch, how many edges would it touch? And how many faces would it touch? By trying the cases of two-dimensional grids and the three-dimensional grids would easily give us the answer. The number of edges it would touch would be 2d, and the number of faces it would be touched would be 2 raised to the power of d. This is again a simple part. One of the major problems in linear grids is how to traverse them in some specific ways. The most important traversal methods, as denoted in his book, would be in row major, column major, snake order, and diagonal order. So for row major and column major, I don't think it's necessary for me to talk about how to implement them, since we can use only two loops to solve them. For row major, the traversal goes something like this, and for column major goes something like this. And the next is about snake order. For snake order, he has shown some code routines like this. But my question is, so can you think of a code routine to implement snake order that would make your code more easy to read instead of using these formulas to solve this trick. And my answer to do this snake order path part would be something like this. I myself feel it's a little bit easier than what Skiena has shown me. Since by using these expressions, so can anyone tell me what this expression means in C++?
If it's true, then B.
Yeah. So if A is true, then B and LC. So the only tricky part about the implementing the snake order is that we have two traversal orders to implement when we are having a odd index in row and when we are having an even index in row. So when we are having an odd index in row, we have to traverse from left to right and otherwise from right to left. So by using an expression like this, we can easily. So this I and 1 to test whether I is an odd number or not. And if I is an odd number, then we can simplify doing something like process ij. And if I is an even number, then it should be I m plus 1 minus j, since we would want to traverse from right to left in this situation. It does the same thing as his code, but I think it might be easier to understand. So the next question is about diagonal order. Again, I feel Skiena's code is a little bit trickier. Diagonal order goes something like this. Here, here, here. For implementing the diagonal order, my solution would be we can first see that we have there are n plus n minus 1 diagonals in the whole grids. Therefore, for each of the diagonal, its starting point would be two cases. I minus 1, I1 in the first n diagonals. And for the rest of the part would be mi for the last n diagonals. For each of these diagonals, how we traverse them would be easy, because each time we only need to handle things like this. So for I equals to 1, I less than 1, I plus plus, and then process x minus I, y minus I. Let me see. No, y, x minus I, y plus I. Because in each of these diagonal, each time the row number is decreased by 1, but the column number is increased by 1. So using approaches like this, we would be rather writing something like So the starting point for x would be I is larger than n. If I is larger than n, then it should be m. Otherwise, it should be I. Or this line could be and the starting point for y would be, if it's larger than m, then it can be something like I. I equals to otherwise it should be 1. And then we just multiply process sx plus 1 and then sx minus 1 sy plus 1 would be okay. So what is left here is the number of elements in each diagonal, which would also be easy to be calculated. So this is my alternative approach to handle the diagonal order, which I feel would be a little bit easier than this one. So after talking about traversal, the next point in his book is dual graphs and representations. Dual graphs and representations are not so useful, in my opinion, because the notion of dual graph originates from planar graph in graph theory. So how many people have learned planar graph in your discrete mathematics course? Or you have never learned? It seems we have not. So what is a planar graph? A planar graph is something that if you draw this graph on a two-dimensional plane, or simply if you draw the graph on a piece of paper, and you can find a way to reorder the vertices so that we will never have intersections of edges except at the endpoints. Such a graph is called a planar graph. And one important notion of planar graph is dual. So basically, it means a planar graph has faces. So this is the face of a planar graph. And since these two faces touch, it can be viewed as two vertices with an edge linked between them. So in graph theory, this is called the dual of this kind of graph. It's something like this. But I don't think it's important to make this notion here, so I just skip this part. Okay, so the next point is triangular lattices. For triangular lattices, it's still very easy. This is a triangular lattice, and we can see that it can be viewed as something like this. So the normal Cartesian coordinate system goes something like the origin is here, and 1, 0 is here, and 0, 1 is here. They're the right angle here. So if we change this right angle to 60, degree, it would go something like so the origin is here, 1, 0 is here, 0, 1 is here, and 1, 1 is here. And then, if we draw all the lines in the form of x plus y equals to d, it would be something like and then if we draw all the lines of y equals to d, it would be something like. So this is just the triangular grid. And we can see it has a very close connection with the Cartesian coordinate system. And again, it would be very easy to calculate its coordinates in this triangular system. In his book, he had mentioned two coordinate systems. One is the triangular or the hexagonal coordinates. About triangular coordinates, it's just something like this. Again, it's easy to understand from a two-dimensional plane. About its geometrical coordinates. So the task of geometrical coordinates is that if we know the triangular coordinates of one point in a triangular grid, how would we know its exact coordinate in a Cartesian coordinate system? So about this part, again, we could be using some simple geometry to solve this problem. But I'd like to warn you that there are some mistakes in his formula here. Since we can see if his formula is correct, then for each of these points, A1, the formula is D. So D is the length of each side of triangle here. So this part is D. So it should be something like D. A plus cosine 60 degree, and then should be D sine 60 degree. It can be seen that if this formula is correct, then the exact y coordinate would be the same for each coordinate in the original triangular coordinate system with their y coordinate equals to 1. But we can see there clearly there are some differences. So there is a mistake here. The mistake lies in that this is not the usual way for us to represent this point. Usually we would be representing this point to 1, 0 instead of a 1. So if you change all of these coordinates back to 1, 0 and 1 minus 1, this formula would then be correct. Again, I would say this part is very easy to understand from a simple geometrical view, and it involves no algorithmic knowledge. So I would assume it would be easy for you to recover all these formulas. And then about hexagonal lattices. Hexagonal lattices are just as easy. So this is a hexagonal grid, or more clearly, this is a hexagonal grid. So another Skinner seems to think that a translation from a hexagonal coordinate system to its corresponding geometrical coordinate would be an important problem. But again, we can see it's very easy by some simple geometry. So I don't know. Do you think it would be useful for me to show you how these formulas are coming out? No? Okay. So again, this is the part he has taught. So the last point is the longitude and latitude. Longitude and latitude, I think all of you know. And one formula that might be useful for longitude and latitude is that if we had known the longitude and latitudes of 2 points, like point A is at longitude, what, and point B is at latitude, what. So how would be as knowing the shortest flying distance between A and B. In other words, we would want to know the spherical distance between A and B. Again, this is a very simple spherical trigonometry problem, and actually it has a name. Let me see if I can recover the name. Sorry. Everson. This actually is what they had taught, because the Haversine formula are just calculating 2 points on a sphere of radius r with 2 latitudes and with two longitudes, and the spherical distance between the two can still be calculated easily from some spherical trigonometry derivations. I also believe this is not actually related to algorithms, so I will just still skip it here. And we would be happy to see, after I skip the derivations of all these formulas, we have already yeah. So now we can see the problems. The reason for me to skip these formulas is that, firstly, I believe it should be easy for you to derive these formulas without my help. And the most important reason is that I don't think the problems he has mentioned are highly connected to the topics he had covered here. So I'd rather talk about the problems rather than the formulas here. So about the first problem, the monocycle. The monocycle goes something like this. It's a cycle with 5 colors, each occupying a 72 degree of the circle. And then for each round, it would rotate exactly 72 degrees, such that we can see in square 1, blue is touching here, and in square 2, white is touching here, and then green. So it goes in a counterclockwise order. The problem here is that we have a two-dimensional grid, and we want to go from S to T. And we would like to know if we can go from S to T with the same color touching the ground at the same time. So this is a problem. And if we try to model this problem using graph theory terms, firstly, we'll want to know how to go from S to T. And this is a simple problem, and we can use any graph search algorithm like BFS or BFS. And then the next problem is how would we go from S to T with the same color touching the ground? So the basic operation we have here is the cyclist starts from some square and tries to move to a target square in minimum amount of time. So again, our objective is minimum. And we can see from minimum, we could go something like BFS or shortest path algorithms. And then the possible action he could take is from any square, he either moves forward to the next square. That is to say, from one square, he can go in either 4 directions. This is normally a two-dimensional grid. Or he remains in the same square but turns 90 degrees left or right. That is to say, we not only need to know the position x, y of the cyclist, but we also need to know the direction he is currently facing at. That is to say, whether he is facing east, west, north, or south. That is to from xy to xyf. This f is where he is facing. Why do we need it? It's because only from x, y, and f would we be able to know what forward actually means here. So from the same grid, if he is facing east, forward actually means going from here to here. And if he's facing west, he will be going from here to here. So where he's facing would determine the outcome of this action. So it also encode this part in the state. So now we know that we would be using x, y, and f to represent the state the cyclist is in. And then each of these actions remains only exact 1 second. This means if we encode it in a graph, this would mean the length or the weight of each edge. And now we know the weight of each edge is unit weight. After reading these 3 lines, we now know this problem is easy, because we can have the graph representation here, and we know the length of each edge is unit. And then what next for us to do is to run a shortest path algorithm from source to the target, the BLK. But the Next point is how do we represent some kind of covered here. And since each of the weight of the edge is unit, and we can use EFS to solve this problem. Let me see. No. I have missed one. Ignore it. Sorry. I have not I have not yet covered these colors here. So another important constraint is that he always starts his ride facing north and with the midpoint of the green segment of his wheel touching the ground. Now what does this part mean? Green segment means here and in the target square 2, the green segment must touch the ground, but he does not care which direction he will be facing. So from the constraint, we know that if he moves between two squares, the cycle would rotate by 70 degrees. And then if he moves along 5 squares, the circle would rotate exactly 1 round. That is to say, from green to green. So that means in order to satisfy this constraint, we not only need to know the shortest distance between S and T, we also need to know whether there exists a shortest path between S and T, and the length of the path should be equals to 0 modulo 5. That is clear. And how do we solve this part? Is that how do we solve this part is that first we can see that there is no relationship between shortest time and the modulo 5 equals to 0 constraint. So we only need to handle whether there exists a path such that its length between x and y equals to 0. Okay. Okay. So to solve this problem, we can encode another part of important information into the graph. That is whether what color is cycle touching the ground here. Now, so we have X, Y, and C. So how do we create the graph here? Actually, it goes something like this. So if the original graph is so a bit difficult, it means if there is in the original graph, if there is an edge from xy to x plus 1 y, and in the augmented graph we have xyc to xy next c. Here, next c would be something like blue to white, white to green, green to black, these kind of things. Is this part clear? Okay. And by using such a graph representation, we now have the original m multiplies n nodes in this graph. And now we have 5 multiplies n multiplies n nodes here. It's a little bit difficult to draw this graph in a clear way. In a clear way, it should be something like can we try to draw it? If there are 4 nodes here, then in the original graph it would be something like this. And now we have this part is blue. This part is white. This part is green. This part is black. And this part is red. So for each square here, we can create an edge between here and here. Since if we move from here to here, the color of the cycle touching the graph will be changing from blue to white. And then from white to green. And then from green to black. And then from black to red here. And for this edge, it would go something like this. So in other words, we are using 5 times of nodes of the original graph to represent the possible colors it can be. And then to solve the original problem is that we start from a grid here from x to y. And then what we would like to know the shortest possible path, or whether there exists a path that starts in green and ends in green. To solve this problem, the starting and end node both to be in the green graph here. And we want to know whether there exists a path, and that's all. So, is there any problem with this part? Okay, we go through the second problem. Star. Star. Again, it seems like a grid problem, but again, I don't think it's related to the grids here. So, do you have another thing? This problem goes something like we have this grid here, and then for each line, we can calculate the largest number in this line. like here we know that the largest number in line A is 5. The largest number in line B is 7. The largest number in line E is 6. So the input of this problem is 12 numbers, each indicating the largest number of each line from A to L. And then we would like to know the smallest and largest possible sums of all digits on the board. At the very first glance, it may seem this problem is a search problem. But again, we can see there are 48 cells here. So searching might not be a good solution, although we can use some. On UVA, there are searching programs passing this problem. Skiena's hint is, can we compute the upper and lower bounds for each digit in isolation? Here I would be talking about how to calculate the upper bounds, since it's relatively easier for lower bounds to be left to you. Calculating the upper bound for each digit is very easy, since we know the upper bound for each cell. So if this cell is in line A and line K, so the upper bound would be the minimum of max A and max K. And for digit 9 here, it belongs to line B, and line I. And so again, the upper bound for this digit would be min max D, max G, and max phi. So calculating the largest possible sum only involves in calculating all of these upper bounds for each digit and sum them all. It's very easy to calculate the upper bound, but to calculate the lower bound may not be that easy. So it's up to you to solve the remaining part. Robbery. I've seen this problem several years ago, and at that time I thought it was a hard problem. The description of the robbery problem goes something like this. We have a time sequence T, and we have a rectangular grid. For each grid, for each time t. For each time t, our known information is whether the robber isn't in the rectangle Ri at time ti. That means at a specific time point t, we have some information of an individual is not at a particular rectangle. So it may be at some other points. The question for us to solve is whether we can determine the exact position of the individual at a time point t, or we cannot. So here we can see 445 means the rectangular grid is is 4 by 4, and 11143 means at time sequence 1. Let me see. Yeah. It means that time sequence 1, the robber is not at rectangular 1, 1 and 4, 3. Means he is not at this rectangular. And 1, 1, 3, 4 means he is not at this rectangular. So it means at time point 1 it can only be here. Another information we know is that at time point 4, he is not at 1, 1, 3, 4. And 4, 2, 4, 4. 4, 2, 4, 4 is here. No, 4, 2, 4, 4. Yes, it's here. Okay, so he's at 4, 1. And then by knowing the robber is at 4, 4 at time 1, and he's at 4, 1 at time 4, we can easily deduce. Sorry, it's easy for us to deduce that he should be at 4, 3 and 4, 2 in time 2 and time 3. Again, I've said I had thought this problem was difficult 4 years ago, but then I found it's not that difficult. So I'll not be talking about the solution of this problem because sorry. Again, there are not many sophisticated algorithms in this part, so I totally leave the algorithm for you to discover. And then the last problem is the Bermuda triangle. This problem is the only problem involving the grid part that we have covered in this lecture. So the underlying objective of this problem is we have a triangular grid here, and we want to calculate the shortest distance between two grids, like from 10 to 2. Can we go from 10 to 5? It's a little bit more simpler than I had thought. From 0 to 7, we only need to calculate the shortest distance between 0 and 7, and that is the length of the straight line connecting these 2 points. And therefore, as soon as we can have a translation formula from this triangular coordinate system to a geometric coordinate, it would be okay. So that's the whole problem. And we can see the success rate. This problem is high. Okay, so after covering these 4 problems, you have 2 days to think about these 2 problems a little bit more. The next thing I'd like to talk about a bit is what we have in the most recent World Finals problem. So I don't know how many people had watched the World Finals here. Anybody? Online? You? So I was retired from ACM ICPC last year, and I don't know for how many years I would be concerning these issues up to now. This year's World Champions was won by St. Petersburg State University of IT Mechanics and Optics, also known as SPB, SPBIT, and formerly known as SPBIFM. This is a very strong team in ACM ICPC, and they are also last year's World Champions, and they also won the World Champion in 2004. And in mainland China, 3 countries have won medals: Tsinghua University, Zhejiang University, and South China University of Technology. We can see that for all teams who have solved more than 3 problems, they'll get a ranking here. And for those honorable mention teams, are those teams unable to solve 3 problems in the whole time constraint. In this lecture, I am aiming to tell you that it's easy to solve 3 problems by using the knowledge we have in this course. So what I'm going to cover will be problem A, problem F, and problem A, B, and F. For problem A, you can read the problem statement here. So for problem A, I just go from the input here. This 3 means we have 3 airplanes. And each airplane, we have n airplanes here. And 2n is less than 8. For each airplane, we have A and B, which means the airplane would be safe to land in the time interval of A and B. Okay? So we would want to determine a permutation or determine an order of how these airplanes are landed, such that such that, say, if we have an axis and airplane A is landed at time t1, airplane B is landed at time t2, airplane C is landed at time t3. So we'll have t2 and t1 here, and t3 and minus t2 here. Our objective is to maximize this ti minus ti minus 1 for each other. It's normal, since usually we would be thinking the maximum time difference between 2 consecutive airplane landing, the safer it would be. So this is the aim we are going. And for the input constraint, we can see it says it's safe to land airplane A at 0:10, airplane B at 5:15, and airplane C at 10:15. So it's okay for us to land airplane 1 at time 0, airplane B at time 7.5, airplane C at time 15. And then the maximum as a minimum over the minimum would be 7.5. And for the next test case, we can see we can land the first airplane at time 0, and then the second airplane at time 20, and then also 20. So how to solve this problem? One question first. Has anybody here tried to solve any of these problems in the previous weeks? Yep. Oh, okay. And one side I'd like to mention is that if you want to solve these problems, you can submit them here. And they have the latest. These problems can be submitted here. Okay, so how do we solve this problem? There is one important property of a specific kind of problems. That is to, instead of minimizing or maximizing over an optimization objective, we would want to know, is it possible with X? Such a problem in computational theory is called a reduction from an optimization problem to a determination problem. If we draw a graph here, like we want to know, say if this is an equation and we have x equals to r here, this is y equals to fx, and fr equals to 0. We want to find which value of x would yield f this part equals to 0. Instead of solving this problem, we will ask a specific problem like, is fx1 equals to 0? So if it is larger than, we know that this r must be less than x1. And then we can ask if fx2 is larger than. That is to say, by asking a series of these questions, we can try to shrink the range from r, from infinity finally to r. And one famous notion is called binary search. How do we solve this problem using these techniques? It's very easy. We are not going to calculate the minimum achievable time. Instead, we want to know whether a time difference of t is achievable So we have a function. Okay, it might be easier for me to copy. So we have a function that returns a Boolean value at time t. Okay, so when we have time t, we can try to put the first airplane landing time at t. If not possible, then we fix the landing time of airplane A at the earliest time it can be. So this is easy. And then for each airplane, we can try to put the airplane landing time at Li at Li minus 1 plus t. So Li minus 1 means the landing time we determine for airplane I minus 1. And it is possible that Li minus 1 plus t may not be a safe landing time for airplane I. So what do we want to do now? It is easy to see if Li minus I plus t is not safe for airplane I, then we use the earliest landing time for airplane I and fix it as the landing time. But it's possible that it's possible that the earliest landing safe landing time for airplane I is smaller than L minus I plus t, which means it is not possible for time t to emerge as an achievable time. So by using these ideas more or less like a greedy algorithm, we could judge whether a time t is achievable or not. And in our main solution, we have something like time low, time high, middle. And with a binary search routine, we can write something like if judge mid equals to true, we can have. So if this time can be achieved, it means the minimum possible time should be less than mid, which means we can assign mid to high. Otherwise, we can assign negative. And this part is okay. So this is how we solve this problem. And now it seems class should be over. And in the next lecture, we will be talking about the problem B and the problem F, which seems a little bit more difficult, but we'll also show we can use topics we've learned to solve these problems. Okay, so see you on Wednesday.